Welcome everybody to our presentation. My colleagues and I are doing this remotely, just like a lot of other people. And I'd like to acknowledge all of my co-authors on this paper and this presentation, Alice and David, Gabriele, Chris and Chris, and all the others who helped make this happen. So we're going to be talking about enabling execution of legacy CFD mini application on accelerators or accelerated computers using OpenMP. And just a bit of background, this presentation is targeting very specifically the aspects that go with porting existing software. So you'll see what I mean by that. So this is the technical content. We're going to give an introduction, certain things about the concepts and methods for accelerated programming. More specifically, we'll focus on OpenMP and we'll go through the target programming paradigm and how that works in OpenMP 4.5. The mini app that we use is this NAS Parallel Benchmark NPB-MZ, and Gabriele will talk more about it. And we will show what the math looks like so you can see the similarity with high performance computing codes that are used in the industry. So high performance computing has been changing constantly. So we started a long time ago when I was an undergrad and grad student with threads and distributed computing, vector processing. Now we're at GPU accelerators and looking at next level. However, most of the legacy software, especially unfortunately due to people like me who programmed it back in the day, it remains in things like in programming languages like Fortran. Good thing about these legacy codes is the tools, but they remain in Fortran. So it's difficult to quickly modify those into the new architectures and changing the programming paradigm. So what you'll see coming up, what the devices look like in accelerated computing and how we leverage using the OpenMP to push this forward, especially for something like an application that's written in Fortran. You will see that this is just a mini app, but a mini app uses the underlying methodologies that go with larger frameworks. And so to some extent, this is the way that you train yourself to go ahead and modify a larger code base. So with that, I'll let my colleague go on.
Yeah, the purpose of this slide is now to show the flow of device-accelerated computing. And by this, we mean we program a CPU, which is endowed with an accelerating device, hopefully accelerating. The device usually provides a very high level of parallelism, but it's not good at running sequential code. Furthermore, the CPU and the device may have completely separate memories. So what we need to do when we program for such a hybrid beast is we need to run all our sequential or just moderately parallel code on the CPU. And only the very highly parallel sections of the code should be offloaded to the device. And furthermore, we need to take care of memory management. So the major tasks when programming consist of identify the kernels and offload the execution to the accelerator. Furthermore, we need to express the parallelism within the kernels. And last but certainly not least, we need to explicitly manage the data exchange between the host and the device memory. So any respectable programming API needs to provide support for those essential tasks. And the OpenMP API is a compiler directive-based API, which provides this functionality. And more about this will be explained in the following 2 slides by my colleague.
Great. So part of this project was to decide how easy it is to use OpenMP to do the offload to the accelerator, because a lot of the codes that we're targeting already have OpenMP in them. So the idea is, can we just come in and kind of use a little bit out of the box what people have been putting into their codes for up to even 20 years and get that to get some decent performance on accelerators. So OpenMP itself consists of a language standard based on compiler directives, runtime library routines, and environment variables. At SC18, the OpenMP 5 standard was released, and that continues to go on. And the standard itself is more than 20 years old. The first accelerator programming support happened in OpenMP 4, and then even more in OpenMP 4.5. And all the reputable compiler vendors at this point have decided they are working towards fully supporting OpenMP5, and that gives us a nice standard for every body to use. And the idea is that with the standard, we gain portability. So our GPU code that we will show in this paper builds on the existing OpenMP code and makes strides towards being portable. At this point, the Fortran compiler support is maturing, but it's not all there yet. And so you'll see in our presentation that we had some differences in what was available in the various Fortran compilers, and this continues to improve as time goes on. OpenMP really tries to take a vendor-neutral approach, and there's a whole consortium of compiler teams, universities, and research laboratories that all contribute to its success.
So as Alice was saying, the OpenMP has been evolving over the years. So the big change in terms of both Fortran and for device programming was in OpenMP 4.0. So that was in 2013. So we have the device constructs. We also introduced a lot of new SIMD constructs and provide some initial support for Fortran 2003. The other thing that's very important is we also added the capability of thread affinity, so you know where your execution's happening. The 4.5, and that was what was used in this work, added some initial things, particularly the task loop and some task prioritization. And that has been fully supported. And as was mentioned in SC18, OpenMP 5.0 was released, and that's particularly relevant for Fortran. Now it has complete support for Fortran 2003. It's having some support for 2008, as well as a lot of support for C++, including C++ 11, 14, and 17. And that should be available. It's available by a number of compilers, and it should be fully available quite soon. And we're quite looking forward to the capability that will offer us.
Okay. I guess now it's time to explain some, to give some explanations about the target, that was the code that was the target of our porting efforts. And this is the SP-MZ benchmark. That's the purpose of this slide, to provide you some background on the SP-MZ benchmark. What is it? It is part of the multi-zone versions of the very well-known NAS Parallel Benchmarks, SP, BT, and LU. Now, in multi-zone codes, complex computational domains are covered with a number of grids, which are also referred to as zones. And the structure of these benchmarks is such that at the beginning of the program, a number of zones are being set up and initialized. Then follows a time-stepping loop. And at the beginning of each time step is an exchange of boundary values between the zones. And then follows a loop over the zones. Within each zone, then, a problem of either type SP, LU, or BT is being solved. And the time step loop is executed sequentially, and that gives rise to coarse-grained parallelism that's exploited between the zones at each time step. And then there is the possibility to furthermore exploit fine-grained loop-level parallelism within the solver routines, within the zones. So there's like a multi-level parallelism within these benchmarks. The SP benchmark, which we chose as the one amongst the three, employs an ADI algorithm and a scalar pentadiagonal solver, therefore the name SP. Now, other than using different solvers, the benchmarks are set up such that the structure of the zones are different. They capture different real-world scenarios in these applications. It is important here to point out that the SP-MZ is designed such that there are many, many even-sized zones. So lots of parallelism available on the coarse grain, and there are no load balancing issues between the zones. It should perform best employing only coarse-grained parallelism only for coarse-grained parallelism. And this actually came back to bite us. But I'm not the one who will have to talk about this. That will come later. So I just want to go on now and explain to you about what approach we were taking when porting the benchmark. And that's so the next slide here that shows up shows you our approach. And what we did is we decorated the existing OpenMP constructs with OpenMP 4.5 offload extensions. And then we added clauses to improve the parallelism. And we also added some additional directives. Regarding source code transformations, we tried to keep them to a minimum. We really did try. For example, we had to change the data layout and the indexing.
So on the left-hand side of this slide, we have the execution flow of the NPB-MZ benchmarks. And so you can see the various steps: setting up the zones, initialize, the boundary exchange with MPI, and then OpenMP is where we're focusing. And I will note that the code that we did generally was using MPI plus OpenMP as before. However, there were a few problems with the compilers, and it's getting better now. But initially, we had a little bit of tuning to do to get the MPI plus the OpenMP to work together properly, only because this was a Fortran code and because of the compiler support. One of the things we did was put our code onto GitHub. I'll note that this project a lot of it happened at a hackathon, and so we were all together, and by putting the code up, well, it was actually on Bitbucket, but with a Git interface, we could easily see the differences that were made in the code going on forward. And you can see that for a lot of the code changes, there were really minimal differences between the CPU version and the GPU version. Here, the CPU version is in pink and the GPU version is in green. So we were able to take a lot of the original code that was already done and make relatively minor changes to get it to work appropriately on the GPU version. And of course, since OpenMP is a directive language, you don't undo anything when you change the directives. If the compiler doesn't support them, they're just ignored as comments.
Right. So I get the fun part of actually kind of going through what we did to the code to actually get some performance out of it. I'll hit some of the pain points as well as show a little bit of the code, direct code modifications. But first, a couple of high points that we hit on when it came to the actual restructuring. The SPMZ code had a couple of small routines that were called inside of nested for loops. Because of some difficulties, we actually had to inline some routines. Now, this isn't the greatest software engineering approach because you could get a little code bloat, but this is what we did to kind of simplify things. It also makes the compiler dependency analysis a little cleaner. Hopefully, this kind of thing will ease up as the compilers mature. We used heavily the OpenMP declare construct, which allows us to define routines as well as constant data as if it should live on the device for the lifetime of the code. We had to do, as Gabriele had mentioned, some fairly aggressive refactoring of the code, mostly of the data structure, to get good data access. When you're vectorizing code, you want stride 1 access of your arrays, and the same thing happens on the GPU. You want to have stride 1 access of your data to have fast reads and writes. So that was a major restructuring of the code that was required there, basically changing loop orientations. The code originally relied heavily on thread private arrays for basically per thread scratch arrays. That really didn't work when we switched from tens of threads to thousands of threads. So we had to refactor the use of scratch arrays to basically have pre-allocated very large arrays for all the threads to be able to use. We also found that we had to exploit not only the nested parallelism inside of each zone, which was the original target of OpenMP in the code, we also had to incorporate some kind of parallelization over all of the zones, because each zone is relatively small. There's not enough parallelism or work to be done on a big GPU, so we had to try to find a little bit of extra parallelism, which was not originally exploited within the OpenMP context. And that falls under what Gabriele was referring to as the coarse graining. So we had to kind of find a way of exploiting the coarse graining while still sticking within the OpenMP. All right, I actually get to show you a little bit of raw code here. So on the left is the original host code written in OpenMP 3, which is just multi-threaded. Think about having tens of threads running at the same time. And on the right is our refactored code. We've left out some of the, whenever you see lots of dots, that's basically, we're skipping over lots of code there just to kind of show you the salient features. So the first part you can notice is the actual change in the OpenMP directives. We had to change from parallel do loops, which is relatively concise, to adding in quite a bit more for the target offloading approach. We also added in no wait statements, which allows us to do asynchronous computing. We'll get into a little bit more detail of that later. And then you also, if you look carefully, you'll notice we had to expand significantly the private declarations. OpenMP offloading was a lot more sensitive to what variables might be declared as private, because those would require us to actually transfer those scalar values between the host and device, and it can be a pretty significant performance penalty. So we had to work on that. Also, digging deeper into the code, you'll notice we had to do some array transposition, basically change the structure of those multidimensional arrays so that we always have stride one access on the inner loop. So these were some of the difficult things we had to encounter to refactor the code to get good performance on the GPU.
So as Alice mentioned, we actually did a lot of this initial work at a hackathon that was held in Oakland, California, but with access to a machine at Oak Ridge. It was their training machine. It's called Ascent, which is essentially the same as their Summit. One thing that gave Power 9's nice performance is that they worked with NVIDIA, and so the NVLink actually works between the CPU and the GPU. Most other implementations is just between the GPUs. And as we alluded to, there were some differences in the compiler support. IBM is fairly mature. It's given reasonable support for Fortran. And the other system that was available is the Cray system at Berkeley called Cori. Initially, that did not have any GPU support, but was motivated by the machine that's following onto Cori will have heavy computation done with GPUs. So they reconfigured Cori to have a number of nodes still using the Skylake CPUs, but a number of nodes having 8-way V100s. So there's a little difference between the two, a little difference in what the CPU is, and also the interconnect is a little bit different. On the Cori system, you just have the NVLink between the GPUs, and then you use PCI connecting between the CPUs and the GPUs.
All right, so now we get to actually look at some of the evolution of the performance on our GPU. So this was, Alice had mentioned that we actually hosted our code on GitHub as part of our hackathon. So in our paper and on the slide here, we actually show the evolution of the performance over time. So think about roughly a week, but also we captured the performance basically by commit. So every time we made a change of code, we could go through and actually assess the impact of the performance. So on the graph we see here, it's not perfectly linear in time, but it sort of shows you the evolution of the performance as we modified the code. I broke it into a couple different categories here. So we have our the first part on the left we call initial. That was basically the raw initial porting of the code from basically pure host multi-threading to GPU offloading. This incorporated things like adding in, removing the thread private arrays, switching to the big scratch arrays, and also doing the changing the indexing to try and get good stride one data access. The end result of that was we only got about a factor of 2 speed up on the GPU, which isn't, we're going for something bigger than that. One thing we did want to point out though is after all of that refactoring, we actually had a % loss in performance on the CPU. So there are sometimes some difficulties and trade-offs you have to make when you do these rather significant refactoring, especially when you have to change the things that would impact cache locality, which happened when we did the scratch array changes. The next category was where we actually started seeing some nice speed up on the GPU was when we switched to asynchronous kernels. This also allowed us to optimize the data transfers between the different zone layers. The asynchronous allowed us to essentially, instead of running one small block of small grid at a time on the GPU, it allowed us to run multiple grids at the same time. Those were the zones, since we have multiple zones that can be executed at the same time. We had our biggest payoff in the third category, and this is when we went through and did a lot more detailed study of the thread private variables. These basically were going through and looking inside the loops and trying to find variables that were getting transferred to the device unnecessarily, and we defined those then as private variables. It has no impact on the host performance, but it did dramatically help us on the GPU, since now we're telling the compiler, you don't have to transfer these to the GPU anymore. You can just initialize them directly on the GPU. The fourth category is some of the platform-specific optimizations, and my teammates were mentioning that OpenMP is designed to be vendor agnostic. And hopefully we're going to get to the point where we're performance agnostic in terms of the vendor. But right now, because of when we did this work, there was still a little bit of performance differences between the vendors. We had two different optimizations that were required between whether or not we were running on a Cray machine or running on the IBM. Hopefully these will go away as the compilers evolve, but we actually get a pretty dramatic improvement when we add in just some minor things such as passing values by passing terms by value for the IBM, or adding in a SIMD statement on the for the Cray compiler. And then our final optimization was unrelated to the actual compilers. This was purely on the code side. That's where we recognized that we had lots and lots of small kernels involved with transferring ghost data between the zones. There's a finite amount of overhead every time you start a kernel and ask the GPU to do something. We found out that the overhead of that was more than the actual cost of running the whole thing. So we just merged a lot of small kernels into one big one. We actually reduced the parallelism, but dropped the overhead significantly. And that's what gave us our last bump of performance, where we start pushing that between 8 and 9 times speed up over the original host-based code. And this was just running on one CPU. And we'll show you multi-GPU a little bit later in the presentation.
Yeah, so this is one of the things that I had to learn when I was participating in this hackathon. First was to profile the code on the GPU and use the tools that NVIDIA was providing. The takeaway from here is that if you profile the code, you'll find the level of parallelism that you achieve given the different kernels. And noticing what the timelines look like, you can guide yourself towards that optimization. Let's just say that this was one of the best tools for us to be able to leverage performance on these systems.
That we found the OpenMP target offload to be a great way to deal with Fortran codes. And there, believe it or not, there's a lot of Fortran codes, and they're good codes out there. And so they need this as a tool to be able to use the GPU effectively. Occasionally, well, we had a slight decrease in the CPU performance, but as Chris was telling us, some of that is just because of whether or not you're trying to exploit vectorization or not. So that's more of a hardware issue than an actual kind of coding issue, because you write the code differently for different hardware a little bit. You try to be as portable as possible, but you can't always. One of the things we're interested as a team in doing now is looking at the larger size class benchmarks, because those are more representative of real codes. And this particular benchmark is characteristic of the algorithms that are used in several real codes. And finally, when we look even further, OpenMP 5.0 features, they're moving towards a lot different ways to optimize even more on the GPUs. Additionally, we did find that the compilers and tools are still a little bit immature for Fortran, but that's moving very quickly. And here's just our performance of the different class sizes, Class C, Class D, and Class A on the IBM Power 9 here. And then also you can see using 42 ranks. And so we did get very good performance out of this, I believe, and it happened very quickly and without a lot of pain. We thank you to ISC for making these virtual presentations possible, and email us and let us know if you have any questions, and we hope you will consider using OpenMP to help port your existing OpenMP enabled Fortran codes to GPUs and other devices. Thank you very much.